Good morning, boys and girls, and welcome back. Today, again, we're going to kind of go back to the beginning of this unit of Chapter 9, and we're going to talk again about Taylor polynomials and Taylor series and their approximations. All right. So if you want, you could all go back and look at the introduction. I'm going to try to make a link posted right above me. If not, it'll be at the very end of the video, but we'll see if it pops up there as you guys are watching this right now. But we're going to go back and talk about, again, creating these series, these polynomials that would represent a transcendental function like sine of x is the one we're going to play with today. The first half of this chapter was, again, we did a bunch of tests on these series to see if they can converge. But once we know that they converge, then we can use these polynomials to represent harder functions that I can't just like go and plug in and evaluate y equals sine x, right? All right, so our goal again today is going to be to create a polynomial that approximates f of x equals sine x. And again, in the introduction video, we did this using the calculator. Now we're going to do this algebraically. All right, so we're going to want something that looks something kind of like this. And if you remember when we did this, it kind of hugged the graph closely towards a centered point and then got away as we went away. So the polynomial wants to look like this, and we're going to center this, though, at x equals 0. And maybe before we get too much further here, let me go back and let's kind of review what we talked about, or let me just kind of show you what we're doing here with a visual demonstration. So if you remember, we have our sine function here, and as we, let's see, it's kind of acting weird on me there, but as we increase the number of terms, allow me to do it. I don't know if it's going to allow me to do it. All right, let's see if it allows me to do it now. As we found more and more terms to our polynomial down here, the more terms we found, remember, the longer that interval of convergence got. Okay, right? The better of an approximator of the function it got. Okay, if I increase the number of terms. And then we also talked about how, you know, instead of always increasing the number of terms, maybe we can shift our center point, right? So I can shift that point to center and still only use 3 terms. And just depending what I'm doing, it'll be, again, it's going to be a good approximator near that point of tangency, near that point of center, we call it. You know, so those are the 2 different ways we can do. We can shift our center, or we can increase the number of terms to become a better approximator of the function. All right? So that's kind of what we're playing around with right here. Again, so in our example here, we're going to try to find a 7th term polynomial centered at x equals 0 that represents sine of x. So if it's centered at x equals 0, we can start to use some knowledge now, and we know that sine of 0 is equal to 0. So our polynomial at 0 should also equal 0. We're going to want those points to be the same. So if I were to plug 0 into this polynomial, that's going to kill off those x terms, and so I would know then that a sub 0 is going to have to equal 0. So I've already found the first term of my polynomial. All right, now that we have both of these functions centered at the same place, at 0, 0, now if they're going to be like each other, then their derivatives should match. So let's go and make the first derivative match and see what we end up with. Okay, so when we take the derivative of p, we end up with a sub 1 plus 2a sub 2x plus 3a sub 3x squared plus 4a sub 4x cubed, and so on. All right. So now again, I'm trying to make my derivatives match. So if f of x is sine x, then f prime of x would be cosine x. And then f prime of 0 at our centered point would be 1. Okay, cosine of 0 is 1. And so because f prime of 0 equals 1, then p prime of 0 should also equal 1. So again, if I plugged in 0 for all these, all the x terms are going to go away. And so I know that a sub 1 should equal 1. So now I've made the center point and the first derivative match. All right? Or I found a sub 0 and I found a sub 1 so far in my polynomial. Now, we're going to do the same thing with the second derivative. So now when we took the second derivative, I got 2a sub 2 plus 6a sub 3 plus 12a sub 4 x squared. I'll forget the x in there. Plus 20a sub 5 x cubed plus 30a sub 6 x to the 6th, and so on, plus 42a sub 7 x to the 7th. And just kind of keeping in mind here, I'm going to go back and write this, but this 2 came from like 2 times 1, right? From the exponent of this one here. And this 6 so far we got because we did 3 times 2, right? And this one here, the 12 was 4 times 3 from those exponents, and this was 5 times 4, and this was 6 times 5, and this was 7 times 6. We're going to want to keep track of that because we're going to find an easier way to write these as we kind of progress here a little bit. But I want to kind of illustrate that pattern that is coming up as we're taking our derivative. All right? But there's that second derivative. Now, I know the second derivative of our function, derivative of cosine, is negative sine of x. And so f double prime of 0 again then is going to be 0. And then so I know that p double prime of 0 should also equal 0, which means that 2, a sub 2 should equal 0, or that a sub 2 then should equal 0. So now I found a sub 2. And now we're going to do this. We still got to do the third, fourth, fifth, sixth, and seventh derivative. That's going to be a little grinder as we get through this. But now let's make our third derivatives match. As I was taking my third derivative here, I just noticed I made a mistake up above here in the second derivative. Just a small one. Instead of writing x to the fourth and x to the fifth, those should have gone down in powers right there. I put x to the sixth and x to the seventh again, so I'm just going to correct that, and I'm going to fix it in this derivative. But I just want to point out I did see that I made a mistake. All right, and so we're going to continue to play the same game. My third derivative, now written correctly, is 6a sub 3 plus 24a to the fourth a sub 4 x plus 60 a sub 5 x squared, and so on. I won't read it all out to you. And so now again I gotta find the third derivative of my function and make it match my polynomial. Okay, so our third derivative of the function is negative cosine x, and I know that f triple prime of 0 then is going to be negative 1. So I know that p triple prime of 0 also has to equal negative 1. So negative 1 then, when I plug in when I plug in 0 to this, I know that 6a sub 3 is going to have to equal negative 1, because that's p triple prime. All right? And so now I can solve this for a sub 3. And if we go back again, look at these patterns. This was, again, the way we got 6 was 3 times 2 times 1. The way that I got 24 was 4 times 3 times 2. This was 5 times 4 times 3. This was 6 times 5 times 4. And this was 7 times 6 times 5. Right? So another way to write this, if I divide by this, I'm going to end up with, instead of negative 1 divided by 6, another way, since these are going to get longer and crazier and bigger numbers, I can say that's going to be the same as negative 1 over 3 factorial, right? So a sub 3 is negative 1 over 3 factorial. All right, awesome. Now let's go match the fourth derivative. All right, so using the same process, there's our fourth derivative of both the polynomial and the function. The function evaluated at 0 is 0, so the polynomial should equal 0, so I get a sub 4 should equal 0. Now I just need to do the fifth, sixth, and seventh derivative. All right, so here's our fifth derivative again now, and you can see that, again, you can see this factorial pattern happening up on top here a little bit. The fifth derivative is cosine of x. Notice that we're swapping between 0 and then 1 and then 0, then negative 1. In this time we're landing on 1 for our function, so in this case the fifth derivative should equal 1 at 0. So I set, plug in 0 and I make it equal to 1. So I get the 120 a sub 5 equals 1, or 120 again is 5 factorial, or a sub 5 should be 1 over 5 factorial. All right, now let me go to the sixth derivative. And in this case here, we would make the sixth derivative match. Again, I get the negative sine x for the sixth derivative of the function. F of 0 is 0, so when I plug in 0, I'm going to get a sub 6 is 0. And now one last time so we can find a sub 7, and then we could write our polynomial. All right, now here is the seventh derivative of our polynomial approximation. And the seventh derivative of the function is negative cosine of x. When I plug in 0, I get negative 1. So the polynomial should equal negative 1. And then so I find that a sub 7 is negative 1 over 7 factorial. All right, so now we found all of our a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 7. So now we can write our approximation for this. If I go back and pull them all from up here, right? I have my a sub 1, a sub 2, a sub 4. So now I can go back and plug them all in to our original approximation, all the way back here in the very beginning. So after grabbing all of those terms, we get, p sub 7 of x. Just so real quick notation stuff. This little 7, this sub 7 here, we will use that on our polynomial approximations, and that indicates the degree that we went to or that we want to go to when we're doing a polynomial approximation. In this case, we stopped, thankfully, at the 7th one, right? But I could have kept going and matched the 8th, the 9th, and 10th derivatives, right? So when you see this p sub some number, p sub n, that n stands for the degree of our approximation. So in this case, we went to the 7th degree, right? It is not the number of terms, it is the degree. But, so we had a sub 1 was, or a sub 0 was 0, a sub 1 was 1, a sub 2 was 0, a sub 3 was negative 1 over 3 factorial, a sub 4 was 0, a sub 5 was 1 over 5 factorial, 0, and then negative 1 over 7 factorial is what we ended with right there. And once you get rid of all the 0 terms, you're going to get something that's pretty similar to that same polynomial. We didn't use the factorials, if you remember, back in that very first one. We said it was, sign was pretty close to x, and then we did, x cubed over 6, and I kind of led us to 6, and x to the 5th over 120, and I really kind of gave us 120 in that introduction video. But this is, and that's 5 factorial, but this is another way to come up with a polynomial approximation, is just by making those derivatives match. It's a bit of work, as you can kind of see there, but it does work. But here, I'm going to give you like the general formula that we're going to use and you're going to want to memorize. That kind of speeds this process up just a little bit. Alright, so a quick bit of definition and recap here. A Taylor polynomial, or a Taylor series, since these are a bunch of terms that are just going to be added together and theoretically to infinity. And that last one we just stopped at 7, but I could keep going. Okay, so these are Taylor polynomials or Taylor series. And these are polynomials that represent other non-polynomial functions, generally some transcendental functions like sine and cosine and e, and but non-polynomial functions. Then, when we have a Taylor series that is centered at 0, like the one we just got done doing, we center that one at 0. Those are known as Maclaurin series. Okay, just know that, and Taylor polynomials or Taylor series can be centered anywhere. But if it's a Taylor series that's centered at 0, then that's a Maclaurin series. So just know that if you hear Maclaurin series, that is one that is centered at 0. And that's important to kind of keep in mind. Alright, so here are the formulas that you're going to want to know and memorize. Get to love them. A Maclaurin series, again, Maclaurin centered at 0, is p sub n of x, where n is the degree, equals f of 0 plus f prime of 0 x over 1 factorial plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 x cubed over 3 factorial. And again, if you kind of go, we kind of showed, that's, how we found a lot of our terms, or a sub 1, or a sub 2, or a sub 3. And again, if you kind of go back and answer over here, wherever it was, if we look at our final answer that we had here, that's where this like 3 factorial, 5 factorial set was coming from, okay? It's from this setup for a Maclaurin series. Alright? So you just want to know the next one will be the 4th derivative evaluated at 0, x to the 4th over 4 factorial, and so on. Alright? If it is not centered at 0, now this becomes our formula. Our Taylor series approximation is going to be, f of c, wherever your center is at, 1, 2, 3, or 4, wherever you're going to center it at. And then plus f prime of c times x minus c over 1 factorial times f double prime of c times x minus c squared over 2 factorial. And so again, the x minus c part is just shifting that function to wherever we want it to be centered at. If you kind of think of our transformations, otherwise it maintains basically this same kind of formula here. So they're very closely related. Real quickly, I want to do just one more problem with you, and then we're done for today. Alright, so we want to find the nth Taylor polynomial centered at c, where f of x is 2 over x squared, and I want an n of equals 4, so that means the 4th degree, or the 4th derivative we have to use, centered at c equals 2. So I'm going to go ahead and use my formula, and there's our formula for a 4th degree, or 4th approximation. And so to find this, I need to find f of c, f prime of c, f double prime of c, basically is all I need to go and find now. So relatively quickly, you should be able to find f of x and the derivatives that you are going to need. Now you just need to evaluate them at c. Alright, so again, we're going to evaluate our derivative at 2, and that's what we get. Once we get those values, then you could go ahead and you can plug them into your approximation. Right? And I'm just going to plug in for that f prime of c, f double prime of c, and my x minus 2c. And I can just simplify that And there is our polynomial that would represent this situation.